Hello and welcome to ControllersTech. Today in this video we will see how to port the U8g2 graphic library to the STM32. This is a very popular graphics library for embedded devices, targeting all types of monochrome displays. We will see how to port this library to STM32 on the STM32 Cube IDE, and use the Cube MX to generate the project. We will also see the implementation on some of the displays, that includes 0.96-inch OLED, 1.3-inch SPI OLED, ST792 based graphic display, and the HX1230 based display. This is why the video is going to be quite long. Here I have all the displays that will be used in this video. The purpose is to show the implementation using all the possible methods, which includes SPI, I2C, bit banging, and even the DMA. We will start with the SH1106 based 1.3-inch SPI OLED display. Let's check out the library first. Here you can see the GitHub page of the U8g2. These are all the devices that are supported, and you can see the full list here. This library only supports the monochrome displays for now, so you can search for the display controller on this page. Alright, let's download this entire library, and extract it. We will copy the required files from it later in our project. As I mentioned, we will start with the SH1106 based 1.3-inch SPI OLED first. Here is how the display is connected to the STM32 F446RE. I have also created a project, and we will configure it now. Let's start with the clock setup first. We will bypass the high-speed clock source. The board has 8 MHz crystal on it, and I want to run the system at maximum 180 MHz. Now we will configure the SPI peripheral for the display. I am enabling the SPI in the transmit-only mode. We do not need any input from the display, so transmitting only is enough for this application. You can see the pins PA5 and PA7 are configured as the clock and data pins. Here I have connected the MOSI pin to the data pin of the display. The clock pin from the MCU is connected to the clock pin of the display. We need to configure 3 more pins, one for the chip select, one for the data or command mode, and one for the reset. The CS pin is connected to the D10 of the MCU. Here I have the pin out for the Nucleo F446. The D10 pin is actually the pin PB6. Let's set the pin PB6 as output, and rename it to CS. Next we have the DC pin connected to D9 of the MCU. This D9 is actually the pin PC7. So let's set the pin PC7 as output, and rename it to DC. At last we have the reset pin, connected to D8 of the MCU. This is actually the pin PA9 of the MCU. Let's set the pin PA9 as output, and rename it to reset. The SPI is configured with 8-bit data size, and the MSB will be sent first. Let's increase the prescaler here to reduce the SPI baud rate to around 2 MB/s. The SPI clock polarity is set to low, and the clock phase is set to 1 edge. Basically the SPI mode 0 is being used. Now go to the GPIO configuration, select all the pins, and set their output speed to very high, or high, whichever is available. That is all we need to configure. Click Save to generate the project. Go to the U8g2 folder we downloaded earlier. Here the C source folder consists of all the necessary files we need, so we will copy this folder in our project. I am copying it inside the drivers folder. Now open the project properties, go to the C++ build settings. Under the compiler setting, open the include path. Here we will add the path to the folder we just copied. Click on the workspace, browse the folder, and save the configuration. Let's build the project once to check for any errors. Alright, there are no errors, so let's proceed ahead. You can search for U8g2 port to find the porting guide. Here is the official guide to port the library to different MCUs. There are examples for STM32 as well. We will start from the beginning. Basically, there are only two things we need to take care of while porting it to different MCU. One is the GPIO and delay callback, and another is the communication callback. These are the two callback functions, which we need to define in our code, and that's it. This is the callback function type, and it is the same for both the callbacks. The delay and message callback handles the delay used in the library. It is also used to handle the timing requirement for the I2C and SPI, in case the software implementation of these protocols is being used. The GPIO messages consist of the setting and resetting of different pins used by the display. For example, the CS pin, DC pin, reset pin, etc. The menu pins are used when a GUI menu is created on the display. We will not use the menu pins in this video. Here is the template for the GPIO and delay callback. We do not need to use all the messages defined here, so let's just copy the initial part of this callback. Now we will only define the messages we need. We do not need this initialization, as the HAL initializes everything for us. The nano and micro delays are used during the software implementation of the SPI and I2C protocols. We are using the hardware SPI, so we will skip these definitions as well. We need to define the millisecond delay, so let's copy it in our function. The HAL delay also provides the delay in milliseconds, so we will simply pass it here. The parameter argument int defines the number of milliseconds. You can also check these messages in the U8x8 header file. Next we need to define the GPIO messages. We are using the pins CS, DC, and reset, so let's define them. Here again the parameter argument int decides whether the pin should be set or reset. So we will simply pass the parameter to the GPIO write function. Similarly, we need to define the DC and reset pins as well. So our delay and GPIO message callback is ready. Next we will see the communication callback. There are some predefined callbacks, in case we are using the software implementation of SPI and I2C, or if we are using the parallel mode. In such a case, we need to define the clock and data pins in the GPIO callback. We will see this case later in the video. For now we will focus on hardware peripherals. These are the communication messages we need to define in the communication callback. Let's copy the initial part of the function from the previous callback. I am calling it U8x8 SPI. Now we will define some new messages inside this callback. The first is the initialization message. It can be used to initialize the SPI or I2C peripherals. In our case, HAL initializes everything, so we do not need this one. Next is the message to control the DC pin. Here we will set or reset the DC pin, based on the parameter's value. Next we have the message to send the data. As mentioned here, the data is located in the argument pointer, and argument int defines the number of bytes. We will simply call the function HAL SPI transmit to send the data via the SPI. The data is the argument pointer, and size is the argument int. Let's typecast it to the pointer to the unsigned integer type. Next is the message to start the transfer process. As mentioned here, this message can be used to enable the chip select pin. We will reset the CS pin to enable the slave device. This is the standard SPI process. Next we have the message to end the data transfer, and to do so, we will set the CS pin. That is all the communication messages we need to deal with. Here you can see a template for the hardware SPI is provided based on the Arduino functions. You can also use this template, just change the functions as per the STM32 HAL. Anyway, we will continue with how we define these callbacks. Actually, these functions should be defined outside the main function. Alright, now we need to call the appropriate functions to initialize the display, and print something on it. Here you can see the startup sequence for the library, so let's open it. We need to first define a U8g2 structure in our code. I am calling it my display. Let's copy all these functions in our main file, and we will modify them according to our display. The first function is used to set up the display, and it changes based on what display you are using. I have the SH1106 based display, and here you can see a lot of functions to set up this display. This display does not have any name, so we will focus on the ones with no name. There are 3 variants of each display type, 1, 2, and F. These numbers basically define the memory used for the frame buffer. 1 stands for 1-page memory, 2 stands for 2-page memory, and F stands for full frame buffer will be stored in the memory. You can see more details about the memory below in the setup reference. For the display with 128 by 32 resolution, 1-page buffer occupies 128 bytes in memory, 2-page buffer occupies 256 bytes, and full frame buffer occupies 512 bytes. These memory occupations change with the resolution of the display, so do check out these setup function references to know the exact size for your display. The F446 has enough memory to store a full frame buffer, so I will use the F variant of the setup function. Let's change the structure to my display. The second parameter is the rotation. Here you can see values for different rotations. I will leave it to the default one. Next is the communication callback, which we have already defined. And at last we have the GPIO and delay callback, which is also defined above. The next function initializes the display, and the next one wakes it up, by disabling the power save mode. Now our display is up and running, so we need to print and draw something on it. Here you can see the U8g2 reference manual. Let's open it. We have the references for different things used in the display. We will only look at some basic ones for now. We need to clear the display. Let's also see this one for drawing a string. After initializing the display, we will clear it first. Here are different functions to print the string on the display, and here is one example for it. Let's copy this. We also need to send the buffer to the display, and here is the function for the same. Let's build the project once. We have many errors here. I forgot to include the U8g2 header file. Alright, most errors are gone now, but there is still one here. Actually the functions I copied are for C++, but anyway I will modify them for the C. The first parameter of these functions will be the U8g2 structure we defined above. You can refer to the drawString and setFont functions for the C in the function reference. Alright, all the errors are gone now, so let's flash the project to the board. You can see the string is printed on the display. Let me add another string below this one. Let's build and flash the project again. Another one is also printed on the display. Let's draw a circle on this display. I will use this function to draw the circle. Here x0 and y0 is the center of the circle, and rad is the radius. Let's build and flash it again. You can see that we have got the required result on the display. So the library is working fine for SH1106 based old display. Now we will try another display. The code will remain pretty much the same, so I will make a copy of these callbacks we just created. I will keep these callbacks untouched, in case someone wants to use them as it is. Now we will interface the ST7920 graphic LCD display. Here is how the display is connected to the STM32 F446. This display doesn't have the dedicated pins for the serial communication, but we can use other available pins for this purpose. The display is powered with 5 volts from the MCU itself, and a potentiometer can be used on the VO pin to control the display contrast. The data or instruction pin acts as a chip select, so it is connected to the CS pin of the MCU. The read-write pin acts as a data pin, so it is connected to the MOSI pin of the MCU. The enable pin acts as a clock pin, so it is connected to the clock pin of the MCU. The CS1 pin, or the PSB pin, must be grounded to use the display in the serial mode. The reset pin is connected to the reset pin of the MCU. We are not connecting the DC pin here, other than that the rest of the pins are the same as what we defined in case of the SH1106. Alright, let's see the changes we need to make in our code for this display to work. This display requires some different configuration for the chip select pin, so let's see it in its datasheet. Here we have the datasheet of ST7920. As mentioned here, the serial mode can be selected by grounding the PSB pin. We have already done that, as explained in the connection diagram. Let's see the details about the serial interface. As mentioned here, the chip select pin must be high for the clock to be accepted by the display. This is unlike the SPI communication we are used to, where the CS pin must be low to enable the slave device. So we need to pull the CS pin high before sending the data to the display. We don't need to make any changes in the GPIO callback. In the communication callback, we need to change the CS pin polarity in the start and transfer end messages. The rest of the callback function will remain the same. Since the DC pin is not being used, we can comment out the messages regarding the DC pin. Now we will change the setup function inside the main. Let's search for the ST7920 here. Here we have the setup function for different resolutions, but I am looking for 128 by 64. Alright, here it is. I am going to use the one with the full frame buffer. The rest of the code will remain the same. Let's build and flash the project to the board. It did not work, so we need to make some changes in the code. Let's use this svariant setup function. Let's build and flash it again to the board. We still did not get the display to work properly. It might be happening due to the high SPI clock we are using. Let's reduce the SPI clock to below 1 MHz. Alright, let's build and flash it again. We have got the display working now. It looks weird because I did not connect the potentiometer to control the contrast, instead the VO pin is left not connected. Let's change the rotation of this display to R3. It did not flip 180 degrees as expected. Let me change it to R2. Alright, the display flipped 180 degrees. So we have successfully interfaced the ST7920 by using this library. The next display we will check if SSD1306 I2C OLED. This is how the display is connected to the F446RE. The I2C clock pin is connected to the clock, and the data pin is connected to the data. We don't have the I2C enabled, so let's open the CubeMX, and enable the I2C one. Select the fast mode to use the 400 kHz I2C clock. The display is connected to the pins PB8 and PB9, so let's configure them as clock and data pins. Alright, that is all we need. Click Save to generate the project. Let's comment out the ST7920 related callbacks. The I2C OLED does not use the CS, DC, and reset pins, so let's remove them from the GPIO callback. Before we modify the communication callback, let's take a look at the porting guide again. As I mentioned earlier, the guide provides the templates for the hardware SPI and I2C communications. Here is the template for the I2C communication, but this is made keeping the Arduino functions in mind. Although there is another template in case we only have one function for I2C transfer. STM32 OLED also has a single function to transfer the data via the I2C, so we will use this template for the display. This is the byte send message, and here we are just copying the data into the buffer. We don't need to initialize the communication, as it is already initialized in the beginning. Inside the start transfer message, we are resetting the buffer index. Finally, inside the transfer end message, we will transmit the data via the I2C. We will call the function I2C master transmit to transmit the data. The slave address for the display is 78 hex, data is the buffer, size is buffer index, and let's set some timeout for this function. We have defined both the callbacks. Let's search for the setup function now. There are separate setup functions for the SSD1306 I2C, so make sure you choose the correct function. I am again using the F variant for the full frame buffer. Alright, let's build and flash the project to the board. You can see the display is working fine with this library. If you are seeing some fluctuations, it is only due to the camera. The display does not fluctuate at all. Let's change this string, and flash the project again to the board. You can see the updated string is printed on the display. So the SSD1306 OLED display is also working fine. Next we will see the last display I have with me, the HX1230. Let's see the connection between this display and Nucleo F446. This connection diagram is for Nokia 5110 LCD, but the same connection can work for HX1232. The only exception is the DC pin in Nokia 5110 LCD, whereas HX1230 does not have the DC pin. The rest of the connection is the same. The clock in is connected to clock, data is connected to data, chip select is connected to CS, and the display is powered with 5 volts from the MCU itself. Let's open the CubeMX again. HX1230 supports baud rate up to 4 MB/s, so I will increase the SPI clock. That is all the change we need to make. Let's generate the project again. Let me comment out the old related functions, and we will define separate callbacks for the HX1230. There is no DC pin used here, so let's remove the message related to the DC pin. Let's also remove it from the communication callback. We need to reset the CS pin when the transfer starts, and set this pin when the transfer ends. Now we will look for the HX1230 setup function. Here I am again going to use the full frame buffer. I forgot to change the communication callback. Alright, let's flash the project to the board now. The display did not work at all. Upon further investigation, I found something unique about the data bits used by this display. Let's take a look at its datasheet. As you can see here, the display needs 9 bits, 1 for the control, and 8 for the data. The control bit decides whether the sent byte is a command, or data. STM32 is capable of transmitting 8 bits, or 16 bits at once. But it cannot transmit 9 bits. We can still manage the 9 bits by keeping track of how many bits have been sent, and how many are remaining. But this is a good opportunity to demonstrate the software SPI implementation. Let's delete the communication callback. Now we will add more messages in the GPIO callback, so to implement the software SPI method. We are going to need the delay in nanoseconds. Don't worry, we don't exactly need a delay of 1 nanoseconds, just perform an operation here, which takes extremely less time to execute. Let's also define the 100 nanoseconds delay. Here I will call the NOP instruction in A for loop. Now we need to define the messages related to clock and data pins. But before doing that, we need to define these pins in our project. Let's disable the SPI in the CubeMX. Instead we will configure these pins as output, and rename them to clock and data. Now go to the GPIO configuration, and set the speed of the pins to very high. Now define the SPI data message inside the callback. Here we will set or reset the data pin based on the value of the parameter argument int. Similarly, we need to define the SPI clock message, and set or reset the clock pin based on the parameter. That is all we need to define in the callback. Now we can use the default software SPI callback available in the library. We will use this 3-wire SPI, as it is used in case of 9-bit communication, where the DC pin is not available. That is it, the rest of the things will remain as it is. Let's build and flash the project to the board again. You can see the display is working fine now. Do not worry too much about this delay time, just set the NOP instruction here, irrespective of what MCU you are using. You can also check the SPI clock timing on the scope. If the clock is too fast, insert A for loop in the nano delay message. Let's change the rotation of the display to see if it accepts the command. It flipped 90 degrees. I will change it to R2, and see again. Alright, now it flipped completely 180 degrees. So we saw how different displays can be interfaced with the same U8g2 library. Some displays have unique features, so we need to make changes in the callback functions. But most of the displays either use SPI or I2C, so we can interface them directly. Now I will demonstrate the use of SPI DMA to interface the display. I will use the SH1106 for this purpose. Let's uncomment the functions required for SH1106. Now we need to enable the SPI again in the CubeMX. So let's disable these clock and data output pins first, and instead we will enable the SPI in the transmit-only mode. Bring the SPI clock down to around 3 MB/s. Now go to the DMA section, and enable the DMA for transmission. The DMA mode is set to normal mode, and make sure that the DMA interrupt is enabled in the interrupt section. That is all. Let's generate the project again. Along with the DMA, we will also see how to use the partial frame buffer to send one-page data to the display. So let's comment out this part, and instead we will use another code to send one-page data at a time. First we set the current page position to 0. Then update the buffer with the data we want to print on the display, and call the next page function. This next page function will send the one-page buffer to the display, and set the position to the next page. This way the display will update one page at a time. This process is slow, but it occupies less memory in the MCU. We also need to change the display setup function to use a one-page frame buffer. Let's build and debug the project to see if it is working fine. I have added a breakpoint inside the do-while loop to see how the data is printed on the display. We have hit the breakpoint, and we are on the first page right now. Let's resume the debugger. We have hit it again. Now we are on the next page, and hence the previous page data has been sent to the display. You can see it is printed on the display. We keep hitting the breakpoint, and with each hit, you can see a new data is printing on the display. So this is how the partial frame buffer works. Only one page is stored and processed at a time, and the loop exits when all the pages have been printed. Let's see how the data is printed when we use a two-page frame buffer. This time two pages are printing at once, and we got the data at a faster rate than before. The two-page frame buffer occupies twice the memory, but it also prints at double the speed. Now let's see the usage of DMA in transmitting the data. We will get the template from the porting guide itself. Here is one template for the SPI DMA, but it uses the Arduino functions. We will modify it as per the STM32 HAL. Inside the send byte message, we need to wait for the DMA completion. We will come back to this later. Let's first create a SPI DMA transfer here. The data we want to transmit is in the DMA buffer, and the number of bytes is the argument int. Once the DMA transfer is finished, an interrupt will trigger, and the transmit complete callback will be called. Inside this callback we will set the variable txdone. Note that I am initializing the txdone with the value 1. That is because before even sending the first byte, we need to wait for the transfer completion. If the variable is initialized with the value 0, this while loop will always wait here, and the transmission will never begin. We can set the variable to 0 after the previous check is passed, so before sending the data via the DMA, the txdone variable will always be 0. Inside the initialization message, we need to initialize SPI and DMA. They are already initialized, so we will skip it. Here the CS pin is set, so we will do the same using the HAL function. Inside the setDC message, we need to wait again for the DMA transfer completion. So let's wait for the txdata variable to be set to 1. Again we need to set or reset the DC pin based on the value of the parameter argument int. Inside the start transfer message, we need to reset the CS pin. Let's remove this as this function is used for the nanosecond delay, and we do not need it in the hardware SPI. Let's set the variable tx done to 0 here. Now inside the end transfer message, we need to again wait for the DMA completion. So let's do that, remove the delay function, and set the CS pin. That is all we need to modify the communication callback. Let's change the setup function to use the full frame, and here we will pass the new callback function. I am changing the string, so it will be easier to identify if the code worked or not. Alright, let's build and flash it to the board. It did not work. Let's debug the project to see the issue. I will run the debugger once, and then pause it. Here it gets stuck at this particular loop. Actually we do not need to wait here, since we are already waiting at the transfer end message. Let's also comment out this part, because if this message is called first, the variable will reset back to 0, and then this loop will never exit. Let's build and debug the project again. You can see the display is working fine now. So we saw how to use the U8g2 library to interface different monochrome graphic displays. We also saw implementation of hardware and software SPI and I2C protocols. You might need to change the protocol implementation based on which display you want to interface. This is it for the video. I hope everything was clear. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.